Okay, for those of you guys who've been following along with me, maybe you've seen a few of these at this point in your semester. If this is your first one, then it won't matter, but usually I'm gonna show you this stuff appear as I go, but the iPad doesn't allow me to unlimitedly undo. And so we're gonna have to use the laser pointer in order to sort this one out. But here's a piece of work that, here's a question that asks you actually four different things. How many joules did the water absorb in this situation? We've got some metal, and the metal is plunged into some water, and they're going to reach a thermal equilibrium. And it's asking you, how much energy did the water absorb? How much energy did the metal lose? What was the heat capacity of the metal sample? And what is the specific heat of the metal sample? Okay. And so remember, the difference between heat capacity and specific heat is that one is for the specific heat is for any amount of the sample. So it's the per gram energy that it takes to raise the substance 1 degree, and the heat capacity is for the object itself. So it's how much energy does it take to raise that whole object 1 degree C. Okay, so the important thing to remember is that the energy that's lost by the metal is gained by the water. And in order to deal with lost and gained, we use a negative sign. So it doesn't matter which one we put the negative sign, it's negative. So it's Q equals negative Q. That's typically how I show it. And so we have to just keep that together as we deal with signs. Okay, so the heat from the metal is 50 grams times specific heat of the metal times delta T, and delta T is 28 degrees C minus 100 degrees C. Okay, and this helps us get Q for the metal. Now, Q for the water is the mass of the water and times the specific heat of the water times delta T of the water. Now, we look up the specific heat of the water. This is not something given in the problem, but you can certainly look that up. So that's 4.184 joules per gram degree C. So now let's go ahead and do the calculation. So 100 times 4.184 would be 418.4 joules per degree C. The grams canceling. And then that leaves me with times 4 degrees C, which is what delta T would be. And at the end of the day, the result is 1673.6 joules, and that's how many joules the water absorbed. Now, how many joules did the metal lose? Now, we know that the value of the heat is equal and opposite in sign, but the word lose already implies the sign. So when I write the answer to this problem, I say that the metal lost that much energy. I don't say that it lost a negative amount of energy. Now then, I've got how many joules the water absorbed, how many joules the metal lost, because they're the same. And now I can figure out the specific heat of the metal. So I use this same formula from before, except now I have Q. And so let's go ahead and put that in there. This time though, I know that Q metal, since I'm using it in a calculation, I need to include the negative sign. And so if I distribute, if this is Q water, then negative Q water equals Q metal. And so I do need a negative sign there. And that's important, right? Because this is a negative, the specific heat should be positive. And since the metal went down in temperature, that means that this value will also be negative. And so you'll see 28.00 minus 100 is negative 72 degrees Celsius. And so when I divide both sides by negative 72 degrees Celsius, then these values become positive. So 1673.6 joules divided by 72 is 23.24 joules per degree C. And then if I divide both sides by 50, I get the specific heat of the metal to be 0.465 joules per gram degree C. Now, how do I find the heat capacity of the metal block itself? I multiply the specific heat times the mass of the block. And so the heat capacity of the metal itself is 23.25 joules per degree C. Okay, that's all there is.